So if you went through the 3 review exercises that I shared with you, you saw an example of a double integral in rectangular coordinates, a double integral in polar coordinates, and a triple integral. Now, here's where we go next. Triple integrals, but in cylindrical and spherical coordinates. Yeah, like you saw in the polar coordinate case, suppose the boundary you're working on is circular in nature. Then it's just friendlier to use polar coordinates. Your limits of integration are usually simpler, and it just makes things a little bit nicer sometimes. Likewise, if we have a triple integral situation where the boundary is 3-dimensional, if the 3-dimensional boundary is cylindrical in nature, we might want to use cylindrical coordinates. If the 3-dimensional boundary is spherical in nature, you might want to use spherical coordinates. So here's what I'm going to do. In this video, I'm going to kind of provide an example of how I want you to think through this. And then, if this was my classroom, you would be doing this on your own. You would be up at the whiteboards with a team, and you would be doing what I'm about to do with spherical coordinates on your own. So you'll see after I do this as an example, I'm going to ask you to do kind of similarly with spherical coordinates. And then, of course, there'll be a video to kind of confirm your thinking. Here's what I mean. All right, so here is the good old X, Y, Z coordinate system. Can you imagine coming out some distance x, going over some distance y, coming up some distance z to get to a point Q in regular rectangular coordinates? Can you imagine it? Now, you can get to that same place, but instead of measuring x, y, z, you could measure in r, a theta, and a z. An r, a theta, and a z. I don't know why when I opened it up in this particular tool, my z, some of my symbols are coming out wonky, but this says r, theta, z. So I hope you see that there's some familiarity here that we're talking about r and theta. Just like in polar coordinates, x, y, this point right here is the point x comma y. You can get to the point x, y by instead starting on the positive x-axis and rotating an angle theta, and then traveling out a certain distance along that terminal side of that angle to get to that same point xy. It's polar coordinates. You see, cylindrical coordinates are really just 3D polar coordinates. So we might want to, you'll see as we work through this, we might need to convert to go from rectangular to cylindrical. As you saw in the last review, we wanted to go from rectangular to polar, so we needed some of those conversions. Likewise, we need some conversions here. All right, everybody, if you come over x and then over y, you're traveling at a right angle right here. The x and the y axis, just like in the traditional view like this, the x and the y axis are at a right angle. The right angle now is down here. So x, y. So in that place, x, y, and then there's this r, what we see is this. It is true that the cosine of theta, the cosine of that angle is the adjacent side, x, over the hypotenuse of r. Now you just kind of have to get your mind around what you're looking at here. Remember, the right angle is here. So adjacent, opposite, and hypotenuse. So cosine of theta is x over r, which means that r times the cosine of theta is equal to x. And then, of course, the sine of theta is that opposite side over r. And so r times the sine of theta is equal to y. So if you know r and theta, you can get x. If you know r and theta, you can get x. Now, what about z? Well, let me do this first. Pythagorean theorem, this is that distance x, here's the distance y, there's the hypotenuse. So, of course, also x squared plus y squared is equal to z squared. So we have all these, not z squared, I'm sorry. Just seeing if you're paying attention. X squared plus y squared is equal to r squared. So this is going to be useful to us. R cosine of theta equals x, just like it was in polar. This is going to be useful to us. This is going to be useful to us. But there's a couple more. What about this one? What's a relationship between x, y, and theta? Well, since x and y are the legs of the right triangle, we could say tangent of theta is y over x. Which means we could also say theta is the inverse tangent of y over x, but let's just leave it in that form. So if we know theta, or if we know y over x, we can get tangent of theta, which means we can get theta because we just do inverse tangent. So there's all these relationships. The point is this. There's all these relationships. R, theta, and x, R, theta, and y, x, y, and r, theta, y, and x. What else? Oh, what about z? All right, this one's the hardest one of them all. This one is super mathematically challenging. See, if you come out x and go over y and go up z to get to that point, how do we get to that point in terms of r, theta, and z? Well, rotate theta, come out r, and come up z. Therefore, we get all of these beautiful relationships. And the last relationship is this. The distance z is equal to z. You had to think about that one, didn't you? But yeah, cylindrical coordinates are just polar coordinates lifted up. Thus the cylinder. Can you see it? Polar coordinates are based on circles because we're rotating, or parts of circles, but circles, we're rotating, we have a radius. But now extend a circle in the z direction. What do you have? A cylinder. So cylindrical coordinates are just polar coordinates in 3D. They're cylindrical in shape. So the z is just the same as it was in rectangular. Z equals z. Okay. Now, we're going to do some work. We'll do some examples of somewhere. It's coming up. We'll do some examples where we use cylindrical coordinates to do something. And then we'll repeat this whole process with spherical.